Hi, so in this video I will talk about a normal distribution and the variance of a normally distributed random variable. So we're interested in a normally distributed random variable, and that's how we express x if it's a normally distributed random variable with mean mu and variance sigma squared. So in this video I will show the proof for variance of x and that it equals sigma squared. So we know that x can be normally distributed with mean mu and variance sigma squared, but where does the sigma squared come from, and how do we get that the variance of x is sigma squared? So that might be an interesting question, or it might not be interesting, but it's part of your assignment, so that's another reason why you might need this proof. So here we want to calculate the variance of a normally distributed random variable x. X is distributed with mean mu and variance sigma squared. Here we want to prove that the variance of this variable x is in fact sigma squared. So in general, the variance is the expected value of the deviation of x from its mean for any random variable x. So e of x, this is the mean of x. So we're subtracting the mean of x, and we're taking the expectation of this and squaring it. So that's what the variance is. It's the expected deviation from the mean squared. And in fact, we also know that that formula equals to this. The proof of that you can find in another video. So it's the expectation of x squared minus the expectation of x squared. And we know that the formula for expectation of x, where x is a continuous random variable, can be expressed as an integral. So if we're interested in expectation of a function of x, named that g of x, that is expressed as an integral from negative infinity to infinity of g of x times f of x over x, where f of x is the probability density function for the random variable x. So you can see that that's how we'll use this formula, the integral, to compute the variance of x. Because variance of x consists of expectation of x squared, so that is a function of x, we could define g of x equals x squared. And here our g of x just equals to x. So if g of x equals x squared, then that expectation of x squared is just integral from negative infinity to infinity of x squared times f of x over x. Again, the f of x is the probability density function of the random variable x. And then expectation of x, all that squared, will be the squared integral expressed here. Again, in this case, our g of x is just x. That's why we have x here, and times the PDF. So you can see we can use those two integrals now to compute the variance of x, which we defined as expectation of x squared minus squared expectation of x. So as I said, we're using those two integrals to compute the variance of x. And in our case, x is a normally distributed random variable. So for a normally distributed random variable, as I said, we defined x as normally distributed random variable with mean mu and variance sigma squared. So for this variable, we know that the expectation of x is equal to its mean mu. So therefore, we already know what e of x equals to, and the proof for that I have in another video. So now we just need to compute the first integral. So we know that this part of the variance, expectation of x is mu, and that is expectation of x squared, so that is just mu squared. Mu here is just a number. It's the mean of x. So now we know that variance of x is this integral here minus mu squared, so now we just need to compute this integral. And since x is normally distributed, we know the formula for the probability density function of x, which equals to this expression here. This is the probability density function for a normal random variable with mean mu and variance sigma squared. So now we can insert this expression into our integral instead of f of x and compute the integral. So here, instead of f of x, we input the formula, and now we want to compute this integral from negative infinity to infinity over x. So this integral looks a bit complicated because we have squared terms here, brackets squared. So first, to simplify it, for simplicity, let's assume that mean is 0, and this sigma squared is 1. So this will cancel because it's 0, and here we would just have 1, and then sigma is also 1, so sigma squared equals 1. So that means we're assuming that x is normally distributed with mean 0, so mu 0 and sigma squared equal 1. So here we have our simplified integral without the mu and the sigma. And in this case, we can use integration by parts to compute this integral. And here we have minus 0 squared, but that just equals 0, so we can just cancel that out. So the trick in integration by parts is to break the terms inside the integral into two separate parts, and then use a formula which will help us to compute the value of the integral. So here, x squared, that equals x times x, right? So we're just breaking that apart as I wrote here. And for now, I just wrote the integral instead of from negative infinity to infinity. I just wrote it right now as a limit from negative n to n as n goes to infinity. Well, that's the same as integral from negative infinity to infinity. So what we're doing here is breaking apart the expression inside the integral into two parts. And because we're doing a trick here, integration by parts, so here you see x will be our f of x, and the second term, you'll see it will be g prime of x. And that will help us to compute the value of the integral. So as you can see, our f of x equals x, so here we have f of x, and our g of x equals negative e to the power of negative x squared over 2. And if we take the derivative of g of x with respect to x, we'll get, so the derivative, we have to bring down the exponent, so that will be minus 2x over 2 e to the power of the same exponent. Minus minus becomes plus, and 2's cancel out, so that's how we get x times e to the power negative x squared over 2. So this is our g prime of x, and we can see this is actually equal to the second expression inside the integral. So basically what we wanted to get here is that the expression inside the integral equals f of x times g prime of x. And then we can do the integration by parts trick. And this part here is just a constant. We can actually even take it outside of the integral. So the trick here is that if we have an integral in the form of f of x times g prime of x, we can actually express it as f of n times g of n minus f of minus n times g of minus n, and minus integral from negative n to n. And now here inside the integral we have f prime of x times g of x. So now we will write out our integral as this longer expression here. So our f of x equals x, and f prime of x is then 1 because derivative of x with respect to x equals 1. And here we have g prime of x, this expression here. And we know that the antiderivative of this is negative e to the power of negative x squared over 2. So remember, this is our f of x. This term here is g prime of x. And this is just a constant. We can take it outside of the integral as a multiplier. So that's what we do here. And now we just write out the integral in terms of this expression. So our f of x is x, then f of n is n. Then our g of n, well, g of x is minus e to the power minus x squared over 2, so g of n is minus e to the power of negative n squared over 2. And f of minus n is just minus n. And this is our g of minus n. And f prime of x is just 1, so here we have like this times 1. So this is our f prime of x, and this is our g of x. Well, and we wrote out the integral this way because it will be easier to evaluate it in this form. Okay, so here this is minus minus, that becomes plus, and then we can see that these terms, if this becomes plus n times minus e minus, well, minus n squared is same as n squared, so we can just try it out as n squared over 2. So we can see these two terms are the same, therefore that equals to minus 2. And here we're just opening the brackets and putting the limit in front of every term. So here this is just, we open the brackets, we left this multiplier outside, but now we're just taking the limit of every term because we can do that with the limit. We can open the brackets and just that will be the same as adding the limit of the sum. So here these terms are the same, therefore this is, we have 2 here and they're negative, so we have the negative sign. And right away you can see here that as n goes to infinity, in the numerator we have n, it goes to infinity, but in the denominator we have e to the power of n squared over 2, that also goes to infinity at a faster rate. Therefore, since the denominator goes to infinity faster than the numerator, the denominator will be much larger than the numerator as n goes to infinity, so we will have 1, and we'll have large n over even a larger number, so that will be going to 0, because we're dividing some large number by a much larger number. And therefore this whole term will be equal to 0, and then we're left with this term and our multiplier. So as I said, this equals to 0, because n goes to infinity, and here we have e to the power of n squared, which goes to infinity much faster than just n. So the denominator becomes larger, so the limit is 0. Therefore, here we have 0, we have the multiplier, and we're left with this integral. So the expression equals to this, and we put the multiplier inside the integral. So remember, what we were deriving is variance of x when x is normally distributed, and we assume that the mean was 0 and sigma squared was 1. So remember, this is a specific case, not a general case. So we found that in this case, the variance of x equals to this expression, and we just evaluated and found that it equals to this integral. Well, you can see here that what is this integral? Well, this is just our f of x, the probability density function of x when mu equals 0 and sigma squared equals 1. So therefore, this integral just equals an integral from negative infinity to infinity of f of x dx. So that is the sum of all probabilities, because f of x is a probability density function, And we know that the sum of all probabilities over the whole range of x must equal to 1, because that's the one property of the probability density function. Therefore, we know that the integral equals 1. So, as expected, we found that the variance of x when x is normally distributed with sigma squared equal 1, well, the variance equals 1, which makes sense. Okay, and I'm just here showing how we can do this in R. So this is the function. This is x squared times 1 over square root of 2 pi, and here I wrote pi approximately as 3.14 times e to the power of negative x squared over 2. So remember, this is our f of x. So this is x squared times f of x, and then I created the x values. So I just made it as a sequence as negative 10, negative 9.99, negative 9.98. They go all the way to 10. And then for each x value, I computed the y values. So I mean, for each x, I computed negative 10 squared times 1 over 2 pi square root e to the power negative 10 squared over 2, and then that for all x in my sequence. And here I actually created the summation, because remember, our variance of x when mean is 0 and sigma squared equals 1, the variance of x is the integral from negative infinity to infinity of x squared times 1 over square root 2 pi times e to the power negative x squared over 2. So that's what I'm doing here. I computed this term for my sequence of x, and then I sum them all together. And here I got approximately 1. Well, not exactly 1, but remember that I put pi as 3.14, which is an approximation of pi. And you can see that I did it from x equals 10, negative 10 to 10. And I still got the summation equal to be 1. Well, that's because for x smaller and larger, these terms equals almost 0, so they don't make a big difference in the summation. Well, and here this is our plot of x, and on the y-axis here, we have x squared times f of x, and we're interested in the summation over the whole range of x. So what we're saying is that the integral, which is the area under the curve, so this area equals 1. That's what I'm trying to show here. That's for x normally distributed with mean 0 and sigma squared equal 1. So we computed the variance of x for a specific case, but we're interested in a general case when x is normally distributed with mean mu and variance sigma squared. So I mean, we don't want to just compute it for when mu is 0 and sigma squared is 1. We want it for the general case, because mean and variance could be any other number. So in this case, we can apply a variable transformation. So here we have a complicated term. And then we have minus x minus mu over sigma squared times 1/2. So let's just define x minus mu over sigma as y. And then dy over dx will be 1 over sigma, because it's derivative with respect to x of this expression, and that's just 1 over sigma. And then dy equals, well, just bring it to the other side, dx over sigma. So the variable transformation is transforming our initial integral, which was in terms of x. Now we transform it in terms of y, where y is defined as x minus mu over sigma. So if y equals x minus mu over sigma, then we need to compute x, because here we have x squared, and we want to express it in terms of y. So we found that x equals mu plus sigma times y, x minus mu over sigma equals y, and here that's all squared. So therefore we have here negative y squared, and here we have dx, but now we want to express it in terms of dy, and we can see that dx equals sigma times dy. Yeah, here I need to have y, because we're expressing everything in terms of y because we changed the variable. And we can see that the limits of integration do not change, because as x goes to negative infinity, well, we just have here x minus some constant, so y will go to negative infinity, and as x goes to infinity, y also goes to infinity, so the limits stay the same. So this is what we're interested in computing. You can see here that these sigmas will cancel out, so therefore this integral equals to this. And remember, this is dy here. I just made a mistake. So because this is a summation, we can split this integral as a sum of integrals. So we can open the brackets here, and since this is a plus b squared, that equals to a squared, which is mu squared, plus 2ab, so plus 2 mu sigma, plus b squared, sigma squared. And that's how we can break apart the integral, because we just have a sum in the brackets. So mu squared is just a number, we can take it outside the integral. Also, 2 mu times sigma is also a multiplier, we can take it outside, and sigma squared is a number, so we can take it outside the integral. So now we just need to compute each of these integrals. But we actually already know what they are. I mean here, well, this is just the f of y, which is the PDF of y if y is normally distributed. So this integral here is mu squared f of y dy. F of y is the probability density function, and as we said previously, the sum over the whole range of the probability density function must equal 1. So therefore, it's just mu squared times 1. Well, let's look at the integral here. Well, this term here, again, is just f of y. So, okay, this equals to this node side of the integral. Y times f of y dy. And this is the probability density function of y when y is normally distributed with mean 0 and variance 1. But then the integral from negative infinity to infinity y times f of y dy is just the expectation of y, which equals mean, which is 0 in this case. So that integral is 0. And this integral here, well, we just computed that because that is the integral from negative infinity to infinity, y squared, f of y dy. So that is just the variance of y, again, when y is normally distributed with mean 0 and variance 1. So that integral equals 1, and therefore that's how we get this simplification here. And you can see that that equals to mu squared plus sigma squared. So remember that we were just deriving right now the first term of the variance, and we found that equals mu squared plus sigma squared, but we had the other term, the minus squared e of x, and that equals to minus mu squared. So therefore, we're left with mu squared plus sigma squared minus mu squared, and that's how we get our sigma squared for the general case.